Hey guys, today we are talking about 9.2 angles in radians. There's a lot of information to cover in 9.2, including a different way of setting up an angle, a whole different way of measuring an angle, along with some other concepts about angles in general. So since there's so much information, let's just hop right into it. So angles that we've been dealing with have been in right triangles. In geometry, you guys spend a lot more time working with angle measures and finding them and the relationships of them and describing them and all of that stuff. In Algebra 2 and really beyond, when you start dealing with angle measures, like in physics, we talk about angles in standard position is what we're calling this. And again, in pre-calc and calculus, you go beyond Algebra 2 level stuff, you have this concept of an angle being what we call standard position, which all we're really dealing with is in standard position is just kind of putting it in the exact same orientation. Because we know in geometry, in our angles, or even in the right triangles we dealt with in 9.1, a 37-degree angle could look a whole bunch of different ways based on where the vertex is and which way the angle is kind of facing. So what standard position does is just kind of puts it in the vertex in the exact same spot. It starts with one side along the exact same spot no matter what angle we're dealing with. That way we're locking those two things in there, and the only thing that's going to change is then that second side to form my angle. So this is what it looks like for an angle in standard position. As you can see, the vertex, I'm going to switch to a highlighter here. The vertex is always at the origin, so the point of my angle, where my angle actually happens, is always at the origin. And then we have this thing called the initial side. Now we know angles always have two sides to them. We never really designated which one was which. In a right triangle, like we had again in 9.1, sometimes it was the hypotenuse and the opposite side. Sometimes it could be the hypotenuse and the adjacent side, or whatever it is based on what angle you're dealing with. But here, we always start with one side on the positive x-axis. So the part that I have highlighted here, that's just what we call the initial side. And that's the one that's always going to be there. It's like the starting point of my angle. And then the other part of my angle is what we call the terminal side. So this other side, the one that actually does the rotating, is called our terminal side. So then the angle that's formed, as you can see here by the arrow, and the letter the variable we're using is theta, would be how far we rotate from the initial side over to that terminal side. And again, just how far we rotate is based on what the angle is that we're trying to graph in standard form. Some other things to note here, since we're putting it in standard form now, we have our different quadrants. Again, this is coming back from geometry. We haven't addressed it a whole lot in Algebra 2. But just describing our quadrants, again here they're labeled quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And that's just based on the where my x values are positive and y values are positive, or positive and negative of any of those ones. Notice here, this is kind of based on, now that we know what standard position means, this makes sense the way that it's labeled, because if you start here at the initial side and you rotate around, notice we're rotating counterclockwise, as you go in that order, that's why the positive x and y values are quadrant 1, and we label them in that order. It didn't really make sense, at least to me, when I had learned this in geometry before I knew standard position angles, why we started quadrant 1 on the top right, and then we went to the left for quadrants 2, 3, and 4. But this is why. That's why we label them quadrant 1, 2, 3, and 4. Some other things to note in here. Obviously, one full rotation we know is 360 degrees, which is what it says down there at the bottom. But then our individual axes break up our circle into 90-degree sections. So here at the initial side, that's 0 degrees. If we don't rotate any far off of that, it just stays 0 degrees. As soon as we hit my positive, let me change my highlighter color. Let's do highlight in blue this time. So our positive, there we go. So as soon as we hit the positive y-axis, we've rotated 90 degrees. As soon as we go halfway around my circle, I've gone 180 degrees. That would just be what would look like just a flat line. If I continue and rotate all the way down here, the next quadrant is 270, and then back to 360. So the important thing here, you're going to have, when we're going through and graphing these, we're going to have the terminal side and the initial side always graphed. But how and where you draw your arrow makes a big difference. Because if I had just, two lines drawn on the initial side, it could either be 0 or 360 degrees, depending on where you draw your arrow. Another thing with that standard position kind of allows us to have is angles of both positive and negative value. And like I had said, my initial side always starts here at this positive x-axis, and as I rotate counterclockwise, because if I started my initial side, I rotate up first, that's a positive angle. Going counterclockwise direction, that would be a positive theta. If I went from my initial side, what I'm drawing now in red, if I go down from that initial side, that would be a negative rotation, so a negative angle. So we actually can now have both positive and negative angle measures. So working with these, if we're trying to sketch the angles, if it's just ask us to sketch it or graph it maybe, it's just going to be kind of an approximation. I'm not going to make you, especially with you guys being at home now, I'm not going to make you bust out a protractor and measure out the exact angles for where things should be. I don't usually do that anyway. As long as you have a pretty good estimation on where that angle should be, kind of definitely in the right quadrant, so which part of my graph it should be in, but also approximately where in that quadrant it should be. So if we look at example 1A here, so if we just go through and kind of label our stuff, this is 0 degrees, 90, 180, and 270. So since we're trying to graph a 240 degree angle, we know it's going to live somewhere in this quadrant. It's somewhere between 180 and 270. Now, suggestions on how you figure out approximately where that should be. If you split up kind of half of my quadrant, would be another 45 degrees. So that's just another way that you can do that. So halfway between 180 and 270 is 225. Right, because 45 plus the 180 would be 225, since each quadrant here is 90 degrees. So you know that the angle that you're trying to graph is going to be at least somewhere in the second half of that quadrant. Now, it's not exactly halfway between those two. It's actually just a little bit closer to the 225, but it's pretty close to halfway. Now I'm going to erase this scratch work there. So that's where my terminal side is. Now when I graph it, I still have to include, you can include the initial side. I know the initial side is where it's supposed to be, so I usually only graph the terminal one, the second one, the one that's actually rotating. But what you do have to do, regardless of whether you include that terminal side on your page, you have to show the rotation. So it doesn't have to be big like that, it could be small right at the origin, but you have to show me which direction it's rotating and when it stops. Because we'll talk about something a little bit later in the notes where we could have angles that spin around in circles, end at the same spot, and have different angle measures. Or, we could also have a very different angle if we went backwards this direction. We could have a negative way of measuring that same angle, but not be 245 degrees. Part B, I'll just talk about real quick. I'll use red, why not? So now that we're doing negatives, there's two different ways of handling this. You could still go through and label everything the way it usually is. 0, 90, 180, 270. And then you're just going to have to know that when you're going negative 170 degrees, that you're going this direction instead of that direction. The other thing you can do if you know you're dealing with negatives and that's all you're doing in this graph, you could also label it the other way around. So this is still 0 degrees. This bottom one down here would be, I'm rotating negative 90 degrees. This would be negative 180 degrees. And then this would be negative 270. If you want to do it that way. Personally, I just remember that I have to rotate the other direction and just know that, you know, I'm rotating down instead of up rather than labeling it backwards. But to each their own. If that makes more sense to you, then go ahead and do that. I don't usually do that. I just wanted to throw that out there for some people who are struggling to make that connection. But here, for negative 170, now that's pretty close to 180 degrees, rotating backwards, but not quite, 10 degrees less than 180. So I don't even bother trying to measure stuff out or like figure out where the halfway point is. I can just recognize that it's almost 180, but not quite 180. So it's going to be a little bit less than 180 degrees. And again, I'm going backwards because again, I'm rotating down instead of up first because it's a negative 170. If it was a positive 170, that would be an angle over here because it doesn't quite get up to 180 degrees. All right, so that's just standard position so far. Topic 1. Topic 2 is radian measure, which you might have seen before. We've definitely seen it on the calculator. I always emphasize, or I guess if I had, you know, we had been together in class and we were doing calculations, and those that I've done Google Meets with and stuff, we've talked about this, checking to make sure your calculator is in degrees instead of radians. It's in that same button. A radian is just a different way of measuring an angle. So there's different ways of doing this. Radians, once again, is something that is a lot more common in upper level math. It makes some different calculations a lot more simple depending on what field you're dealing with. Upper level physics stuff, we do use radians occasionally. We do still use degrees as well. And we will work on converting back and forth between those two. But basically what radian is, it's a different way of splitting the circle up. So we know in degrees, they, not necessarily arbitrarily, but they just chose that a full circle is just split up into 360 individual pieces. And each of those little pieces is what they're calling a degree. Now a radian is a little bit different. It's based on the radius of the circle. So if I was able to, and I can't on my iPad, if I was able to take this radius, take this length, and I put a string and made it that exact same length. But then I took that length of string and laid it around the outside of my circle here. So again, the two blue lengths there are the exact same. One is just in a straight line, one is curved. That angle that's formed on the outside of my circle, right there that I'm labeling theta right now, that is what's defined as 1 radian. Again, the radius is the same as the length around my circle. So that's where the actual angle for a radian comes from. Now, going through and kind of what makes that nice is that we know quite a bit about the length of the outside of a circle. We know that a circle is 2 times pi times the radius to get its circumference. All right, I'm kind of jumping around here a little bit. So that's 2 pi, I don't know why I put it as capital, times the radius. So that means that 1 full revolution, if I have r as my radius, would just be 2 pi radians, because 2 pi r equals radians. And again here, my radius, since that is the length around the outside, if I just divide by that r value, that is 1 full rotation. So that means going back up here, in 1 full rotation, there are 2 pi radians, which is approximately 6.28 radians. And you can see here that this is just a different visualization of it. Here I've still got my standard position radius. I've got that same length around 1, so that's 1 radian. That same length here is 2 radians. Another side of the radius, 3 radians. And you can see right here, right there, half the turn, that would be approximately pi. Well, I'm sorry, it'd be approximately 3.14, but pi radians. Here's another length of the radius, 4 radians, 5, 6, and then a little bit more. So that's what radians are. They're a little bit different. They're a little bit weird. It's a whole different way of splitting up the circle. Now, when it comes to standard position for in radians, 0 is still 0. If I haven't rotated at all, I have gone 0 radians. But we know, ooh, that was weird. We know that a full rotation is 2 pi. That's the radius of a circle, so if I go 1 full rotation, that's 2 pi radians. So that means that 180 degrees, half of the rotation, would be half of 2 pi, which is just pi. So if I'm going halfway between 0 and pi, this would be pi over 2. And then halfway between pi and 2 pi would be 3 pi over 2. And it's basically just taking it and turning it into a fraction, where if this is 0, I've got, here I'll trace it with my highlighter since I can do that. I've got 1/2, 2 halves, which reduces to just 1, 3 halves, 4 halves, which reduces to just 2, in radians. So if you're trying to figure out where your stuff, like where the angle that you're trying to find belongs, 15 over 4, right, 15 over 4, would be 8 pi over 4 plus 7 pi over 4. An easier way of doing it, I guess you could do it this way. 15 over 4 would be 3.75 pi. And since each rotation here is 2 pi, it's almost 2 full rotations. So that's where those two, how I split this up over here, which I didn't really explain, I just kind of did it here. 1 full rotation, if I'm in terms of fourths of pi, pi over 4s, there are 8 of those, right? Because 8 pi over 4 reduced to 2 pi. So this here, this is 1 full rotation, and then another 7 pi over 4 on top of that. So it's a little bit weird because we have 1 full rotation, that would be the 8 pi over 4, and then almost a whole nother rotation with 7 pi over 4. So that's one way of doing it. It's very, very confusing. It's very, very odd and takes a lot of getting used to. The other way you could split this up is if you know that half of your circle, so half of this rotation from 0 over to pi, is that, and you're dealing with something in terms of fourths of pi, what you could do is kind of make dotted lines on here that splits it up into pi over 4 pieces. So like this whole rotation, 1 full turn would be 2 pi. So halfway would be pi. A quarter of the way would be pi over 2. So then what I'm going to do here in orange, each of these pieces is a pi over 4 slice. So all of these little dots in there, or each of those is a pi over 4 slice. So as you can kind of follow along, I'm going to trace over this blue spiral that I had. My initial piece, and I'm going to switch to something a little easier to track. Let's do this, I don't know, let's see how pink shows up, and I'll zoom in. So since I'm trying to go 15 pi over 4s, This first piece would be 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4. So I've done one full rotation. 9, 10, 11, 12, 13, 14, 15 pi over 4 pieces. Because again, I know this is 0, this would be pi over 2, based on how we have our quadrants laid out. So halfway between those two would be a pi over 4 slice. It's very weird, I understand, it is very different. It takes a lot of getting used to. This, along with what we'll cover in the next section, are what most Algebra 2 people, or most Algebra 2 students' least favorite topics are. And it is what it is. So if we did that new idea here for this next angle, here we're still dealing with 0, this is pi over 2, this is just pi, this is 3 pi over 2, and this would be 2 pi. We just put our regular standard angles in there. So now we're doing negative 2 pi over 3. Negative 2 pi over 3. So with this one, we're trying to split our kind of into, if you think of it in terms of like slices of pizza or slices of pie, we're trying to split it up into thirds. So if one full rotation is 2 pi, half of the rotation would be pi. So if we're splitting, basically what happens is this top rotation here. If I'm splitting it up into thirds, it would be approximately that. Not quite perfect, but approximately. So, that's not good there. Not perfect, but again, for our approximations, close enough. And I really like this one. Let's try and straighten that out a little bit better. So then, as you rotated, every time you hit one of those dotted lines, that's the next third of pi. So if we're going backwards, 2 pi over 3, that would be going down first. So this is 1 pi over, oops, I don't like that straight line. I'm going down 1 pi over 3, 2 pi over 3. So this line right here would be negative 2 pi over 3. Different, weird, understandable. It's understandable that it's confusing. For this last one, we're in radians now, and it's just labeled to us not in terms of pi, but just a number. And this rads, or sometimes just rad, is the abbreviation for an angle measured in radians instead of degrees. Degrees has the little circle above it, like 180 degrees, that little degree symbol. Rad is just what we use for radians, or rads in this case. And the best approximation that I can do, the best way of explaining this, it'd be to take those same angle measures we had before, pi over 2, pi, 3 pi over 2, and this is 2 pi, and just convert them into decimals. There's no other way. I mean, there's a way I could do it where I could try and show you how to convert it into radians and try and work backwards that way. But the simplest way for us would just be to get a decimal approximation for each of these different measures. So we know, like pi, that's 3.14. 2 times pi, 2 times 3.14 is 6.28. If you used a calculator, 3 times pi divided by 2 is about 4.71. And then pi over 2 is about 1.57. So since I'm trying to graph 4 radians, 4 rad, I'm going to be somewhere between, I'm down here in quadrant 3, so somewhere between pi and 3 pi over 2. And again, looking at where it is, it's almost halfway, not quite perfectly halfway between the two, but it's definitely in the middle somewhere. So I'm not going to be super picky about where exactly it is and finding, how much exactly is in between the two of them and working backwards that way. We just know it's about halfway between pi and 3 pi over 2. Okay. Continuing along. I'm not super concerned with this next section. I don't want to spend a lot of time on it because it's going to be a long video anyway. Stating the quadrant or axes where these are, where the angles are, where they terminate. Basically, it's just if you can do it in your head, awesome. If you need to do a little sketch out, that's fine too. Basically, all that's asking us to do is for a different angle. You're just telling me which of the four quadrants is that angle terminal on, or if it's one where it's on a quadrant actual axes, you would just tell me, oh, that's on the positive x-axis, or oh, that's on the negative y-axis. So I just want to do a couple of them with you. Again, I usually just sketch it out if it's not obvious to you on where that is. So for 157 degrees, we know it's somewhere between 90 and 180. And since it's positive, it's rotating this way. It doesn't matter where in the box it stops. So I would call this a quadrant 2 angle. And that's all there is to it. For negative 2 pi, again, that's one full rotation backwards. But my terminal side is on the x-axis here. So I would say the positive x-axis. If I was going to get descriptive, if I was going to get specific. If it was just stated as, state the quadrant, you would just say none of the above, it's an axis angle. And kind of the same thing with all the other ones. I would just go through and do a quick little sketch of it to try and approximate where it is. So here, quadrant B, negative 75 degrees, is not even down past that first quadrant angle. So this would be a quadrant 4 angle. But once again, I don't want to spend a ton of time on it. You just need to sketch it out if it's something that's not obvious to you. All right, second to last topic. Coterminal angles. I've talked about this idea already, especially with our positives and negatives. And one of the problems up above, I talked about it's possible for angles to do like a full rotation and then some. We actually did one of those. Example 2A, we had one that rotated one full rotation and then another rotation after that. So what we could have happening, we could have two angles that have the same terminal side but have different measures. And it could be either, again, because they go different directions, one's positive and one's negative. It could be that one does a full rotation and then another little bit to match back up with it. But anytime we have two angles that have the same initial and terminal side, we just call those coterminal angles. So when we have something, here we're starting with 120 degrees. That's this right here. Nice. Those are our initial and our terminal sides. We're just trying to draw in some other coterminal angles for that angle. So one obvious one is that I could go backwards instead. So instead of going positive 180, positive 120, I could go backwards 240 degrees. Another thing I could do is, like I talked about earlier, you could do one full rotation and then keep going to get to get back with 120 degrees. Now here, all we're doing is basically, this is 480 degrees. Now how I'm getting those angles is basically all I'm doing is adding or subtracting a full rotation from 120. So this one in the middle here, I took 120 minus a full rotation, so I went backwards a full rotation, and that's what got me my negative 140, or my negative 240. Here, I did my 120 degrees plus a full rotation, so a full 360, and that's where I got my 480. So for the questions down here, how many of the angles could be coterminal with 120? As many as we want. We can keep adding and subtracting 360 degrees if we wanted to, as far as we wanted to, as many times as we wanted to. Could your calculator give you a list of all of them? Yeah, I guess if you wanted to get fancy with it. 120 plus or minus 360n would give you them, but we never really use that. The easiest way to do this for finding coterminal angles is literally just you grab your calculator, whatever angle you're starting with, add 360. Whatever number you started with, subtract 360, and it will be that easy. In radians, the big difference here is that instead of adding or subtracting 360 to get a full rotation, because 360 is not a full rotation in radians, 2 pi is the number that we have that represents one full rotation in radians. So here we're dealing with, it's hard to see on my page, but this is 5 pi over 4 is the angle that we're starting with. So again, if we wanted to go same thing, I want to go backwards instead, I would be doing 5 pi over 4 minus 2 pi. Now for that, your fraction game will have to step up a little bit if you have forgotten it. I'm actually going to move this over here so I have something to work down. We have to find a common denominator. 5 pi over 4 minus 8 pi over 4. So this would be negative 3 pi over 4 for that angle. If I wanted to go 5 pi over 4, 5 pi over 4, and then a full rotation on top of that, it would be my 5 pi over 4 plus 2 pi. Eek, that's an ugly 5 there. Over 4 plus, 8 pi over 4. So you end up with 13 pi over 4 for that angle. Same answers here. I'm not really concerned with them. There's an infinite number of them. Don't need to worry about your calculator to find the other coterminal pieces. So one way that this is the most common way that you're going to be given a question in terms of coterminals. They want us to state two coterminal angles for each given angle. And specifically, they want one positive and one negative coterminal angle. Now that doesn't necessarily mean you take your angle that you're given, one time you add 360, one time you subtract 360. You have to make sure that you have one angle that's coterminal that's a positive number, and one angle that's coterminal that's a negative number. Now sometimes, like in this first one, for part A, if you add 360, you get 400 degrees, and that is a positive coterminal angle. If you do 40 minus 360, you get negative 320, which is a negative coterminal angle, which is awesome. You can just add 360 and subtract 360, and you have a positive and a negative coterminal. However, if you try doing the same thing with part B, if I add 360 here, I end up with a negative 440 degrees, which is fine. It's a negative coterminal angle. But then if I went back to my 800 degrees, my negative 800, and subtracted 360, I would get a bigger negative number. I still need one of my coterminals to be positive. So what you can do is then just keep adding 360, which in this case would be negative 80 degrees. That's still not positive. That's another option for a negative coterminal if you wanted to say negative 80 instead of the negative 440. But I have to add 360 again until I hit a positive number that is coterminal. 280 is the first positive coterminal angle. So that's just one little wrinkle to it. Just be aware of that. Sometimes you might have to add 360, or if it's a really, really big positive number, you might have to subtract 360 a bunch of times before you get a positive and a negative. And then with my radian measures, here again, kind of the same idea. I'm not going to do part C because we already literally did that exact same problem. Add and subtract 2 pi, which in this case would look like 8 pi over 4. here for my 9 pi, that's my angle in radians. If you don't see a degree symbol, that implies that it's radians. So sometimes we write the RAD afterwards, sometimes we don't. If you don't see anything written there, you assume that it's a radian measure. If it's measured in degrees, it'll have the degree symbol on there. So here, with 9 pi, all you have to do to find your coterminal angle, since it's in radians, you're just adding or subtracting 2 pi. Now, since this is a pretty big number, relatively, I'm going to start by subtracting 2 pi. So one option for a positive coterminal is 7 pi. But then I have to keep going until I hit a negative coterminal angle. So minus another 2 pi would be 5 pi, minus another 2 pi would be 3 pi, minus another 2 pi would be pi. And then if I finally subtract off another 2 pi, the first time we hit a negative angle is negative pi radians. And then any of these could be used as a positive coterminal angle with 9 pi. When you're dealing with something with radians where it's not an angle that's in pi, it's not in pi form, you could still do the same thing and keep subtracting off 2 pi. Easier way of doing it would be to add or subtract 6.28. Just use the decimal approximation for that. It's the same thing we did when we were graphing when it was in just a decimal form instead of a pi exact form. So here you should end up with, when you add 6.28, you get 11.28 radians. When you subtract 6.28, you get negative 1.28 for those two there. All right, so that's coterminal angles. Just adding and subtracting the full rotation. The last part here is our way of converting back and forth between degrees and radians. And that is something that's going to be useful for us because all of you, I guarantee you, no matter how much this makes sense, you are more comfortable working in degrees. And if I give you something in radians, you're going to want to be able to convert it in degrees in order to work with it. But what goes one way, we have to also be able to go the other way. So here we have our method for translating, converting between the two different forms. And basically, it all takes advantage of the fact what one full rotation is in each angle measure. So a full rotation we know in degrees is 360 degrees. We know that one full rotation in radians is 2 pi. So that lets us convert between those two. That lets us approximate how much each of those things are. So in this relationship here, 2 pi radians is equivalent to 360 degrees. That lets us figure out approximately how much each of these things are. So 1 radian, if I divided by 2 pi on both sides, 360 divided by 2 pi would be 180 over pi, if I solve for radians, which we like to approximate, nope, not a 5, it's supposed to be the 5, 57.3 degrees is what approximately 1 radian is. So I don't know why I have this next one in there, just extending it. I'm not really concerned with what 7 radians is. I mean, sure, 401.1. But really what one radian is converted to degrees is the best approximation for it. But what this method has given us is our conversion factor. That's what lets us convert from one to the other. Now, if you have taken chemistry, if you took chemistry, you guys did a lot of unit conversion problems, and having a conversion factor is very important. So knowing like that 12 inches is equivalent to 1 foot, if you had that fraction, 12 inches over 1 foot, you know that it's equivalent because they're the same exact length. So if you multiplied something by that factor, you could convert from inches to feet or from feet to inches. And this is the same idea here. If I'm trying to convert from radians to degrees, I want here, since my degrees are up top and my radians are in the bottom, if I multiplied by this fraction, an angle that's in radians, my radians would cancel out on top and bottom, and I'd be left with something in degrees, because my degrees would be up top. So without having to go through and repeat myself over again, going from degrees to radians, which you don't have necessarily, I think, as big a need to do that. But again, in upper level science and upper level math, we do this a lot. Or if you were given something in degrees, you might have to convert it into radians. And basically all we're doing is just the reverse of that. So all we're doing is the reciprocal of it. We know that pi and 180 are equivalent to each other because they're both a half turn of the circle. So if I wanted to convert instead into radians from degrees, I would multiply by pi over 180, because that's going to leave me with a radian up top and my degrees canceling out on top and bottom. In case you're concerned, which you really shouldn't be, pi over 180 is 1 degree in radians, which is approximately 0.017. But again, we never really use that. It's more so this multiplication factor at the bottom. So converting between the two of them, really it's just 180 and pi, or pi and 180. But whatever you're trying to convert into is the thing that should be up top. So here we're trying to convert from degrees into radians. So that means we want to multiply so that radians are up top. And I suppose we could put it up there. So now what happens is my degrees cancel out, top and bottom, and now I'm just left with radians. So I've got 135 pi over 180, and the only thing we have to do, it would be to simplify. So this reduces, they're both divisible by 45, in case you're wondering. 3 pi over 4. Now, one other way that you can do this, if you're not feeling super confident in your simplification, so your reduction skills, what you could do for this, if you just do on your calculator, everyone, or most everyone has this option. If you did 135 divided by 180 and hit equals. Actually, let me grab my calculator and do that so I can show you what that decimal is. 135 divided by 180, we get, 0.75. I should have known that from the fraction. 0.75. Not always that pretty. Sometimes they're ugly. But from there on your calculator, everyone has a button that looks like this, or at least most people do. And where it is on your calculator could be different, depending on what it is. But that button, it's our F to D button, lets us convert back and forth between fractions and decimals. So if you do that, if you go from here, after you typed in, you got the 0.75 right away before you hit anything else, if you just do that conversion, that fraction to decimal button, it tells you, oh hey look, the simplified version of that fraction, or that decimal, is 3 over 4. So then all you would need to do is throw that pi right back on top. 3 pi over 4. Alright, I'm just going to do one of these, just so that it's all the same thing, multiplied by pi over 180, and then simplify. I want to do one in radians, just so you guys get used to it, or see it. Because again, this is a long video already. For the last one here, I'm going to just do example A for example 2. Here we're trying to convert from radians into degrees. So that means, because right now this is in radians, so I want to multiply, and I want degrees as my answer. So my degree measure then would go up top, and my radian measure should go on the bottom. Because, again, I'm going to have my radians cancel out. And actually, in this case, my pi cancels out, and I can reduce 180 by 2 and get 90. So after all of that, negative 90 degrees would be my answer. That's my angle in degrees. Now these don't always convert nicely. Usually if you have something in terms of pi, you'll get a nice clean answer because your pi is almost always going to cancel out. Like here again, if you multiplied by 180 over pi, pi cancels out. I reduced that by 2 to 90, so 9 times 90 would be 810 degrees. Nice and easy. When you don't have pi in your answer, you're still going to multiply by 180 over pi. That's going to be just multiply straight across 360 over pi. And you'll just have to, that's weird looking, you'll just have to approximate what that is. So you'll hop on your calculator, 360 divided by pi, and you should get 114.6 in this case degrees. I'm fine with you leaving it at either of these. Just make sure if you're measuring something in degrees, you've got the degree symbol in there. If you're measuring something in radians, you don't have the degree symbol in there. I know that that's a lot of information, and I went through it pretty quickly, but I wanted to try and keep the video as short as possible, even though it's probably a really long video anyway. You've got a couple of days to kind of decompress and process this information. On Thursday of this week, or at least sometime before then, I will be posting another video for 9.3, which is starting to get into the unit circle, and different trig measures of angles. But if you have any questions, please reach out. Please let me know. I'm available for Google Meets that many of you have been taking advantage of, and that's awesome. And it's really been helping you guys. Those who haven't been doing that, let me know if you're willing to give it a shot. It is really beneficial. Otherwise, if you're just more comfortable just sending emails back and forth or chatting through Remind, that's fine as well. Just don't just sit there. If you're frustrated and you're confused, don't let it fester. It's even more difficult now than ever for me to know that you're struggling. So you need to kind of step up a little bit and just ask. If you advocate for yourself and ask me for help, I will not stop until you understand what you're supposed to be dealing with. Okay? I'm hoping everyone is doing okay. I know this is less than ideal situation, and it is what it is. We got to make the best of it, hoping the best for everybody else. I'll talk to you guys later.